In principle, in quantum mechanics, this table can be here in the next office over at MIT at the same time, but it's never the case because these large superpositions, they never exist in reality.
Could you explain why quantum computing is a fundamental problem?
So basically the idea of quantum computers in a simple way, which is not entirely accurate, but largely accurate, can be understood as follows. Basically, in a classical computer, all information is represented as sequences of zeros and ones. And in quantum computer, what you do, you replace classical bits by quantum bits, the systems which can be in a superposition state, right, in 0 and 1. What gives quantum computer is their power is that you can prepare this kind of massive, large superpositions of these quantum registers. Right, so you can take a quantum register and instead of processing just one input, you can process many inputs at once. This is sometimes called quantum parallelism, right? And it gives rise to all of these kind of famous examples like Shor's algorithm and things like this. But these big superpositions are actually, it turns out to be very hard to create in a lab. And the reason is somewhat fundamental. All objects around us, like this table, for example, it's in principle made of quantum particles. In principle, in quantum mechanics, this table can be here in the next office over at MIT at the same time, but it's never the case because these large superpositions, they never exist in reality. They all is effectively described, these large objects are described by laws of classical mechanics. So to build a quantum computer, what you need to do, you need to make a large superposition of all of these qubits. By large, you could say, for example, thousands of qubits. And this is something which does not occur in nature. So the mere idea whether such large superposition can ever be built has never been done. So it's a very important fundamental question.
Basically, like you're describing, because these states don't exist in nature, like these large superposition states, they're very unstable and very hard to produce, right? And that's what everybody's struggling, whatever system they're using. So if you look at transistors, one of the big drivers of the success of transistors is that they were able to create the p-n junction, which maintains a very interesting situation at the microscopic level passively. The p-n junction is passive, so it would be something
because
like...
it has non-linearity.
Exactly.
Right.
It doesn't, there's basically just the material, just the doping of the material gives you those properties. So you don't have to, for example, externally force them. So the question is there a trick like this that has been discovered yet in quantum computing, or is that yet to come? So has anybody found a hack? The way that like the p-n junction is something like a trick.
So to answer this question, given that we understand the challenge, right, it's useful to go back to mid-90s, where we are now still. And what happened at the time was that there was some early excitement about quantum computers, that people showed that quantum computers can potentially, for example, simulate physical systems much better, much faster than classical computers can do. It was early work by Richard Feynman, and then there was also important contribution by Seth Lloyd at MIT. And then there was a work by Peter Shor, who showed that quantum computers can solve an important practical problem, factoring, faster than any classical computer, at least any known algorithm in a classical algorithm can do. But at the same time, during this time, mid to late 90s, there was also very wide skepticism whether quantum computers can be built ever. And the reason is precisely because large quantum objects can just not be created. And one specific issue there is connected to error rates in quantum operations. So going back to what I already discussed, in some way, quantum computer can be viewed as a kind of version of an atomic clock. And atomic clocks, as we discussed, are very precise. Atomic clock can basically keep the time or keep the kind of a phase fixed to 1 to the, better than power to 10 to the 19, basically. It's an extremely precise system. But the problem is that in a quantum computer, what you need to do, you basically need to start with qubits, which you can think about as atomic clocks. But then you need to start doing operations on these qubits. You need to basically start doing quantum logic. And this quantum logic has to be also extremely precise. For example, to execute useful algorithm at scale, people believe that you need error rates something like 1 to the 10 to the 9 or something, one in a billion or better.